Welcome to a journey into the profound and the unseen. Our story begins not with a star, a planet, or even a galaxy, but with a motion. An ancient, relentless, and mysterious motion. Right now, our home, the Milky Way galaxy, along with thousands of our cosmic neighbors, is being pulled through the void at a staggering 2.2 million kilometers per hour. We are not just drifting, we are being summoned. The source of this summons is an enigma, a gravitational anomaly so vast it defies easy explanation. We cannot see it directly, for it hides behind the glittering, dusty veil of our own galaxy, but we feel its presence in the very fabric of space-time. Scientists have given this cosmic mystery a name that evokes its power and scale: the Great Attractor. This is not a story about what we see in the night sky. It is a story about the shadows, the invisible forces that govern our cosmic destiny. It is a hunt for the unseen universe. To understand our journey towards this unseen force, we must first understand the fundamental laws of our universe. In the early 20th century, Albert Einstein gifted humanity a new vision of reality. He proposed that there is a cosmic speed limit, an ultimate velocity that nothing with mass can ever reach: the speed of light. It is the universe's most sacred law. Light travels at a constant, unwavering 299,792 kilometers per second in a vacuum. This isn't just a number, it is the bedrock of physics. But Einstein's genius didn't stop there. He revealed that space and time are not separate entities, but are woven together into a single four-dimensional fabric: space-time. Imagine this fabric stretching across the entire cosmos. Massive objects, like stars and galaxies, don't just sit in space, they press down upon space-time, creating curves, dips, and wells. What we perceive as gravity is not a pull, but the effect of moving through this curved geometry. A planet orbits a star because it is following a straight path through space-time that has been warped by the star's mass. Light, too, follows these paths. It always travels in a straight line, but when space-time itself is bent, the path of light bends with it. This is how we can see stars that are technically hidden behind our sun. This elegant model of the universe works perfectly, but it also presents a profound question. If the speed of light is the ultimate constant, and gravity is simply the shape of space-time, how can we measure a universe that is constantly in motion, constantly changing? And more importantly, how could this framework lead us to a mysterious movement that seems to go against the grain of cosmic expansion? In the 1920s, astronomer Edwin Hubble made a discovery that forever changed our perception of the cosmos. By observing distant galaxies, he noticed something peculiar about their light. It was stretched, shifted towards the red end of the spectrum. This phenomenon, known as redshift, was the first concrete evidence that the universe is not static. It is expanding. The fabric of space-time itself is stretching, carrying galaxies along with it, like raisins in a rising loaf of bread. The farther a galaxy is from us, the faster it appears to be moving away. This became the standard model of cosmology, a universe born from a singular event, the Big Bang, and expanding outward ever since. For decades, this model held true, but in the 1970s and 80s, astronomers began to map the motions of galaxies with unprecedented precision, and they found a deviation, a stunning anomaly. Our local group of galaxies, including the Milky Way and Andromeda, was not just moving apart from everything else as expected. It had what scientists called a peculiar velocity, a motion that was independent of the overall cosmic expansion. We, and everything for hundreds of millions of light years around us, were streaming in the same direction, towards a specific point in the constellation Centaurus. The Hubble expansion was the background music of the cosmos, but this was a powerful, overriding signal. It was as if our entire section of the universe was sliding downhill into a colossal, unseen gravitational valley. This is how the idea of the Great Attractor was born. It had to be a concentration of mass on an unimaginable scale, tens of thousands of times more massive than our entire galaxy, exerting a gravitational pull so immense that it could override the expansion of the universe in our local vicinity. There was just one problem. When astronomers pointed their telescopes to that region of space, they could see almost nothing. The culprit was hiding. A hiding place of the Great Attractor is a region of our own sky that astronomers ironically call the zone of avoidance. It is the plane of the Milky Way galaxy itself. This band, filled with dense clouds of gas, dust, and a thick concentration of stars, acts like a cosmic curtain. It blocks visible light, effectively blinding our optical telescopes and hiding whatever lies beyond. For decades, this cosmic blind spot kept the Great Attractor a theoretical ghost. How do you study something you cannot see? The answer was to look at the universe through different eyes, using wavelengths of light that our eyes cannot perceive. Scientists turned to X-ray astronomy. Massive clusters of galaxies are filled with superheated gas that glows brightly in X-rays. By scanning the zone of avoidance with X-ray telescopes, astronomers could pierce through the dust and detect the faint glow of these hidden clusters, revealing parts of the structure responsible for the pull. Simultaneously, radio astronomers developed a powerful technique. They tuned their telescopes to a specific wavelength of 21 centimeters. This is the natural emission frequency of neutral hydrogen gas, the most abundant element in the universe and a primary component of galaxies. Radio waves at this frequency can pass through the galactic dust unimpeded. Surveying the sky with radio telescopes allowed astronomers to map the location of thousands of previously unknown galaxies, painting a more complete picture of the mass concentration in the direction of the Great Attractor. Finally, infrared surveys provided another crucial piece of the puzzle. Infrared light, with its longer wavelength, is far better at penetrating dust than visible light. By looking in the infrared, we could confirm the existence of the galaxies first hinted at by the radio surveys. Slowly, painstakingly, using this multi-wavelength approach, astronomers began to lift the veil. And what they found was not a single monstrous object, but a sprawling, complex web of galaxies and clusters, all converging on a central region dominated by a massive structure known as the Norma cluster. The Great Attractor was not one thing, but a vast gravitational basin. Yet even with all these discoveries, a problem remained. Even after adding up the mass of all the newly discovered galaxies in the Norma cluster and its surroundings, the numbers didn't add up. The visible matter, the stars, gas, and dust we could detect, accounted for only a fraction of the mass needed to explain the tremendous gravitational pull we were experiencing. The Great Attractor was still missing most of its mass. This is where the story turns from the unseen to the truly unknowable. The missing mass, scientists concluded, must be made of dark matter. Dark matter is the single greatest mystery in modern cosmology. It is a substance that does not emit, reflect, or interact with light in any way. We cannot see it. We cannot touch it. Its existence is inferred only through its gravitational effects on the matter we can see. It is the invisible scaffolding of the cosmos, the ghost in the machine. And scientists believe it makes up roughly 85% of all matter in the universe. The Great Attractor, therefore, is not just a cluster of galaxies. It is a monumental concentration of this elusive dark matter, with visible galaxies merely sprinkled throughout it like cosmic dust. It is the gravitational heart of an even larger structure, a supercluster of galaxies we call Laniakea, a Hawaiian word meaning immeasurable heaven. Our Milky Way is but a tiny speck on the outer fringes of this colossal supercluster, all flowing inward towards its gravitational center, the Great Attractor. And the scale doesn't stop there. More recent mapping of the cosmic web has revealed an even larger structure nearby, the South Pole Wall, a vast filament of galaxies stretching over 1 billion light-years. These discoveries reveal a fundamental truth. Our universe is not a random scattering of stars. It is an intricate, interconnected web of visible and dark matter, with superclusters linked by filaments surrounding vast, empty voids. The Great Attractor is simply the closest, most dominant node in this cosmic network. So, we are being pulled towards a colossal, invisible mass. Does this mean our galaxy is doomed to be consumed in a cosmic collision? The answer, surprisingly, is no, because there is another invisible force at play, one that opposes gravity, a force that is pushing the universe apart. We call it dark energy. If dark matter is the universe's scaffolding, dark energy is its engine of expansion. It is a mysterious repulsive force, an intrinsic property of space itself that is causing the expansion of the universe to accelerate. Our ultimate fate, and the fate of the entire cosmos, is a grand tug-of-war between these two invisible giants. The gravitational pull of dark matter, embodied by structures like the Great Attractor, tries to pull everything together. The repulsive push of dark energy tries to drive everything apart. The outcome of this cosmic battle will determine the end of everything. Scientists have envisioned several possible scenarios. The first is the Big Freeze. If dark energy remains constant, it will eventually overcome gravity on the largest scales. The universe will continue to expand, accelerate, and cool. Galaxies will recede from one another until they are lost beyond a cosmic horizon. Star formation will cease. The universe will fade into a cold, dark, and empty eternity. A more violent possibility is the Big Rip. If dark energy grows stronger over time, its repulsive force could become so powerful that it overwhelms not just the gravity between galaxies, but the gravity holding galaxies together. Then the forces holding stars and planets together, and finally, even the atomic forces holding matter itself together. The very fabric of reality would be torn apart. The third scenario, once thought likely but now less so, is the Big Crunch. If the force of gravity, from all the dark and visible matter, were to eventually win, it could halt the expansion and reverse it. The universe would begin to contract, collapsing back in on itself, heating up until it ended in a singularity, perhaps birthing a new Big Bang in an endless cycle. The current evidence leans towards the Big Freeze. It seems dark energy holds the winning hand. The pull of the Great Attractor, while dominant in our local neighborhood, is ultimately losing the war against the relentless, accelerating expansion of space-time. Our journey has taken us from the speed of light to the edge of cosmic oblivion. We started with a simple motion and uncovered a universe dominated by shadows. The Great Attractor is more than just a destination. It is a profound lesson. It teaches us that what we can see with our eyes is merely the foam on the surface of a deep, dark, cosmic ocean. We live in a universe governed by forces we are only beginning to comprehend. Our existence is shaped by the delicate balance in a cosmic struggle between the pull of dark matter and the push of dark energy. The hunt for the Great Attractor is a testament to human curiosity. It shows our relentless drive to peer through the veil, to map the shadows, and to understand the fundamental nature of reality. We may never reach the Great Attractor as the expanding universe carries it away from us, but the act of chasing it, of seeking to understand these invisible giants, is what defines our place in the cosmos. We are the universe's way of knowing itself, even the parts that hide in the dark.